hello to everyone who is watching on YouTube. I'm just waiting for a few people to join the session in person. So maybe we can get started in like 5-10 minutes. If no one else joins, then we'll get started nonetheless. So I'll mute myself for 10 minutes. Hi Gomti, we were just getting started. So, yeah, since like I was just waiting for a few people to join the session in person. So anyway, since you have joined, we can get started now. Uh, so yeah. So hello everyone. Just to reintroduce myself, I'm Lakshya Saggi, the problem-solving TA for the NPTEL Special Topics in Algorithms course, and this is going to be our 10th. This is going to be our 10th session or at least the session about the 10th week's topics. And in this session, we are going to talk about the topics covered in this week, which were like linear programming and a bit about like fully polynomial time approximation schemes. So yeah, and like previous sessions, again, we'll be first doing a summary of whatever was discussed in this week's lectures, and then we'll proceed to some problems, some practice problems, which can help you solve the weekly assignments. So yeah, without further ado, I guess we can get started with discussing the problems. So I'll just share my screen then. So Gomti, I hope my screen is visible. Can you once confirm in the chat, please? Okay, I guess yeah, I guess like oh okay, it's visible. Yeah, thanks a lot. So yeah, we can get started. So this is, as I said, week 10, and in this week, like in the first few sessions, like initially this week, there were discussions about like again discussions about the knapsack problem, which was shown to be weakly NP hard. In like last week, we showed that the knapsack problem is weakly NP hard, and we discussed in last week like what do we even mean by like weakly NP hard and strongly NP hard problems. So yeah. So what was the knapsack problem? Let's just revise that. So uh, in the knapsack problem, suppose we are given as input n items which have like weights a1 till an, and all of the items also have some prices p1 till pn, and we have a size like b size knapsack. It's essentially a bag which has the size of b. So now in this bag, essentially you can carry items with total weight up to like capital B. And now what we have to output is a subset of items uh, such that uh, the sum of prices is maximized. The sum of prices of the items which you are carrying is maximized, subject to the constraint that the total weight in the bag is at most B. You have to select some items so that the total weight of the item does not exceed B, and you have to maximize your profits on, let's say, the prices of the items which you have collected in the bag. And this was shown to be the knapsack was shown to be weakly NP complete. Uh, However, there exists a pseudo-polynomial time algorithm for knapsack. We discussed last time what do we mean by a pseudo-polynomial time algorithm. So maybe we let's just first discuss like let's just first discuss a pseudo-polynomial time algorithm for knapsack problem. And yeah, the algorithm will be essentially based on dynamic programming. So this was discussed in the lectures also, but anyways, let's just revise this because it's going to be useful for us. So yeah. So suppose we maintain a table A where which is indexed by two variables I and P. So A I comma P like the A I comma P the I comma P entry of the matrix or the table A is essentially stores the minimum size of a set of items from like first I items uh, such that profit of those items is at least small p. And if no such set of items exists, then we define like this table entry to be infinity. And it can be seen that the value a1 comma p is essentially like out of only the first item, you have to have a profit of at least small p. And so when will this profit be available to us? It will only be available to us when uh, yeah when the profit p1 of the first item is actually greater than equal to the p which we have here. And so for all the values p less than equal to p1, we can store the first item and like satisfy these conditions. So a1 comma p is equal to small a1 for all p less than equal to p1, and it will be infinity otherwise, because otherwise there does not exist any such set of items. Yeah, and then we can actually, so we have some base case conditions which we can easily solve, which we can easily initialize, and then we'll have a recursive stage, or like if you have the base case, and how do you define the bigger entries. And it's not too hard to see that a like I plus 1 comma pth entry. So plus 1 comma pth entry essentially says that out of the first I plus 1 item, you have to select the smallest size subset of items such that the profit is at least p. So here, if we don't select the I plus 1th item, then it's just, so there are two ways: either you include the I plus 1th item, or you don't include the I plus 1th item. If you don't include the I plus 1th item, then this entry is just ai comma p. And the second case is, suppose you have included the I plus 1th item, uh, then at least ai plus 1 weight is added to uh, your entries, and then how much profit you have already accumulated because of I plus 1 item, you have accumulated a profit of pi plus 1. So now the further profit which you need to ensure is just p minus pi plus 1, and this much profit needs to come from like the first I items, because I plus 1th item has already been chosen. So these are the two entries, so these are the two cases, and you have to take the minimum of these two cases because we want to minimize the weight. And that's why using this kind of a relation, uh, and because of this base condition, we can actually initialize all the table entries. And now what will our knapsack like solution look like? The solution to our original knapsack problem will be just the maximum profit achievable with a bag of size B. So it's just uh, so here we just need to find the maximum P such that out of the first n items, the items uh, we have to select the minimum size set, like, or let's say the a n comma p entry should be less than equal to capital B. So maximum such profit such that this condition is satisfied will be our knapsack's maximum profit which we have. And it's not too hard to see that correct, because we have initialized the base case and the recursive case accordingly. And the runtime for this algorithm, what will it look like? So the runtime will be essentially, we'll need to uh, find out all the entries of the table. So it will be like table size and time multiplied by time required to update an entry of the table. And note that time required to update an entry of the table is nothing but it's we just need to take this minimum of two values. So this will be just order one. So the time, yeah. So just the so the time required will essentially be proportional to the table size only. And what's the table size here? So table size is nothing but so we have n items. So the number of rows in the table will be n, and what will be the uh, width, or like the number of columns in the table. So it will be just the maximum profit which one can accumulate. And what's the maximum profit which one can accumulate? It's nothing but if the profit of all the items is like, suppose let's say maximum capital P, and there are n items, so n times P is the maximum profit which one can accumulate. So that's why the table size is nothing but like n multiplied by n times. And that's why this is something like table size n square p, and time required to update an entry is just order 1. So the runtime of this algorithm is n square times p. And yeah, so that's why if p is if p is expressed in unary, then it's a like pseudo polynomial time algorithm. Yeah, because like if p is expressed in unary, then this is a polynomial time algorithm, but this is not polytime if p is expressed in binary, and that's why this is a pseudo polynomial time algorithm. And now suppose, yeah, so this is fine. Like we have this algorithm which is pseudo polynomial time. But now suppose someone asks us that, okay, like uh, I need to find an explicit polynomial time algorithm, but I'm fine with you not giving me the like the output should not necessarily be the maximum possible profit, but it can just be a good approximation to the maximum possible profit. Since we have been talking about approximation algorithm for a while, that's why here we'll be talking about finding a good approximation while maintaining strong polynomial time. And for this, then there was discussion in the lecture videos about like how can one like use these kinds of DP-based ideas and this kind of algorithm to obtain actually a polynomial time algorithm, which is also a good approximation. And the idea is essentially, on a high level, the idea is essentially we have these. So let's just first look at maybe why this algorithm takes so this algorithm takes like n square times p. And what is p? P is just uh, like the maximum price of any item. So note that if p is large, so if the disparity between let's say like if one item has a very large price or profit associated to it, and others have some small prices of profit associated to it, then still this value is going to be quite huge. What one can do is maybe try to say that, okay, maybe I'm not exactly worried about like exact values like 1 to p as the prices, but we are fine with bucketing these prices into small buckets, like maybe and those buckets are something like which are entirely up to us. So let's say like I can bucket all the items which have like a price between 0 and p by 2 in one bucket, and all the items which have price from p by 2 to p in second bucket. And similarly, I can refine those buckets even further. And using those buckets, now this capital P becomes smaller, but then we are losing some sort of precision because now we are approximating or like we are bucketing the actual cost by some other cost. And this is essentially the high level idea behind the approximation algorithm discussed in the lectures. So what we do is suppose we are given any epsilon greater than 0, and we define this k as epsilon p by n. So this epsilon p by n will essentially be the bucket interval which I was talking about. And now for each object, we can define a new price pi prime, which will be just the original price divided by k, and we just take the greatest integer function over it because we don't want to overshoot the actual price. And if now we use the pseudo polynomial time algorithm to find the most profitable set, and we just output that set. And it was shown in the lectures. We'll not be going over the proof here again because yeah, because these sessions are not actually substitutes for lectures. Yeah, I'll be assuming that you guys have seen the lecture videos, and these are just kind of brief revisions of the lecture video. And it can be shown that the profit of the solution of our algorithm will actually be uh, greater than equal to 1 minus epsilon times the profit of the optimal algorithm, which means our solution is kind of a 1 plus epsilon approximate solution or something. And what will be the runtime for this algorithm? So runtime will be, like we told, that the runtime will be n squared times p, but now p is replaced by this many number of buckets, p over k, and it's uh, smallest greatest integer function. And this is nothing but p over k is just n over epsilon. So then the runtime is just n cube multiplied by 1 over epsilon. So what essentially we obtain is a 1 plus epsilon approximate uh, an algorithm which gives a 1 plus epsilon approximate solution and runs in time like n cube over epsilon. And now this epsilon is up to you, like whatever epsilon you choose, uh, you'll get the appropriate approximation guarantee as well as the runtime. If you choose epsilon, let's say as 0.5, then you get a half approximate algorithm with a runtime of 2n cube. And similarly, if you choose epsilon as 0.1, then you get like a 0 point or Yeah, here you get a 0.9 factor. But now, like since you're closer to the optimum, you will be paying more runtime cost. So the runtime will be like n cube divided by 0.1, which will be kind of 10 n cube or something. Yeah. But the good thing is like this algorithm is polynomial in n, which is the input size, and 1 over epsilon. So since this epsilon is the like this epsilon is like relevant for the approximation ratio. So like if we try to improve the approximation ratio, since the runtime is polynomial in 1 over epsilon, the runtime does not get a lot worse. Like it does not get much worse as compared to like improving the approximation guarantees. And these kinds of algorithms are called uh, fully polynomial time approximation schemes, or in short, FPTAs. So what are FPTAs? So FPTAs are essentially algorithms where approximation algorithms which can output like a 1 plus epsilon approximate solution in runtime, which is polynomial in input size as well as polynomial in 1 over epsilon. So I hope this makes sense. So Gomti, if you have doubts at any point of time, like feel free to ask in chat and I'll try to answer them to the best of my capabilities. So yeah, so this is what is called FPTAs. And yeah, like usually like obtaining FPTAs for all the NP-hard problems is not always possible, but yeah, an ideal goal usually is to obtain like if a problem is like let's say NP-hard or NP-complete, then a good goal for solving that problem is like just obtaining maybe here FPTAs for that problem. Because in FPTAs you can get as arbitrarily close to the approximation factor as you want, because this epsilon is up to your choice. And you just pay like an extra cost of like polynomial in 1 over epsilon in the runtime. So yeah, yeah. And just as a revision of what has been discussed, what kinds of approximation algorithms have been discussed till now, till previous week and right now. So last week there were in the lecture videos also there were discussions about two approximate algorithm for vertex cover. Then there was a 7 by 8 approximation algorithm for max 3 sat, which was then de-randomized using method of conditional expectation. Then we also discussed a half approximate algorithm for max cut, and de-randomize it using we again de-randomize it using method of conditional expectations. Then there was discussions about like two approximate algorithm for metric TSV, and then we also had a 3 by 2 approximate algorithm for metric TSV. And also like there were discussions about log n approximate algorithms for set cover as well. And today we discussed like till now we have discussed FP task for yeah knapsack. Uh, maybe I'll just mute myself for a minute. I'll just come back in a minute. I have to get some water. Yeah, sorry for the break. So, after discussing all of this, there comes a very natural question. Okay, like for this two approximate algorithm for vertex cover, we try to apply different concepts like we try to relate it to matchings. Then for the 7-byte approximation algorithm, for max result we had different ideas. For metric TSP we had different ideas, and like yeah. So for all these algorithms, it seems like for the different problem at hand, we need very different set of ideas for solving or finding an approximation algorithm for the problem. But is there a more general or more uniform way in which we can, a more standard way in which we can try to derive approximation algorithm for some problems? So of course, like it's not like one hammer to solve all your problems, but one tool which is usually useful in a lot of problems is using linear program based approximation algorithms. So linear programs in short are called LP. So LP based approximation algorithms have found like a lot of uses in a lot of problems. It's not like they'll always solve all the problems at hand, but yeah, for a large class of problems, usually the best approximation algorithms are found using linear programs. So, so that's why like it is very like this kind of this paradigm of like linear program based approximation algorithms is like very important in the context of approximation algorithms. So yeah. So what is a linear program like? So just like I just described the relevance or why are we even studying this, but yeah, what even is this linear program? So so what is a linear program? So LP is an optimization problem where we have a set of variables and the goal is to optimize the linear function of these variables subject to a set of linear constraints. So pretty simple definition on a high level. It's just that what's a linear program? You have a you have a set of variables. Objective function is linear in those variables, and the constraints, and there are some constraints which are also linear in those variables. So, for example, say this is example of a linear program. Suppose x1, x2, x3 are variables, and then suppose we have to minimize 7x1 plus x2 plus 5x3. It's a linear function. The objective function. This is the objective function, which is again linear in these variables and subject to the constraints. And these constraints, you can see these constraints are also linear in the variables x1, x2, x3. So because yeah, so there is a set of constraints, and this is the and this is the objective function. Yeah. So this is an example of a linear program. So these y1, y2s, and yeah, this primal linear program, we'll discuss about this a bit later. Like what are these y1, y2, and what do we mean by primal linear program? So this discussion will come a bit later. But yeah, for now, this is the linear program. Like minimize this subject to these constraints. Yeah. And yeah, maybe yeah. So the idea is okay. Uh, why are we even talking about? Okay, I think I uh, just a second. Oh, okay. I think I okay. No, it's coming a bit later. Yeah. Uh, yeah. Okay, it's coming a bit later. Never mind. Yeah. So okay, so why are we even studying linear programs? Maybe it will come a bit later. Like, why are we talking? Like, how do we use linear programs to design approximation algorithm or something? But for now, let's just understand what linear programs are and what are some of their properties, which will be very useful for us later on. So we know what is a linear program, and let the optimal value of the linear program be, let's say, LP opt. Then also like it's not always necessary that this linear program will be feasible, because it might be that these set of constraints when taken together have no solution, and it also might be the case that like even if it is feasible, uh, then this value, the objective the value or the optimal value of the linear program may be unbounded. It need not be finite. It may be possible that the uh, optimal solution to the linear program is plus infinity or minus infinity, uh, even if the program is feasible. So suppose like, so for now, let's just suppose that this linear program is feasible and its optimal value is finite. And let's say the optimal value is LP opt. then can we get some interesting lower bounds on LP opt? Like, suppose this is the problem at hand that we have to solve this linear program, and then can we obtain some interesting lower bounds on LP opt? And then there were discussions about like there were discussions about this in the lecture videos about uh, the dual LP. So this is so this is the initial linear program given to us. So this is called a primal LP, and then one can always obtain a dual to this linear program, which is called the dual LP. And how does one obtain the dual LP? So this was discussed in lecture. On a high level, like I can just talk about it again. So essentially, uh, how do we obtain dual LP? So if we want to obtain a lower bound, let's say on the objective function of this linear program, how can we obtain the lower bound? So suppose we are given these set of constraints for the problem. So what one can do is one can take a linear combination of let's say these two set of constraints. So one can say that I multiply this constraint with the value y1, this constraint with the value y2, and then add them. And then we know that this side multiplied by y1 plus this side multiplied by y2 should be greater than equal to 10 y1 plus 6 y2. And if I always ensure that the coefficients of x1, x2, x3 do not exceed these values 7, 1, and 5 respectively, then I can say kind of that 10 y1 plus 6 y2 will always be a lower bound for the, or yeah, will always be a lower bound for this problem. And then one can try to one can again form a a linear program which has these sets of constraints as these coefficients of x1, x2, x3 in terms of y1 and y2 not exceeding these coefficients, and also the objective function will be to maximize the value of 10 y1 plus 6 y2. So I'm just describing on a very high level how do we make the dual LP here. You should watch the lecture videos to get an exact idea of how does one form a dual linear program from the Q1 primal LP. So yeah. So the dual linear program helps us obtain a good lower bound on the solution of the primal LP. And actually, interestingly, this is a very this was a very big result. Like when this theory of linear programming was being developed, this result is called strong duality, and which says that actually it's not just that dual LP is a good lower bound for primal LP. It's also the case that the if the primal LP and the dual LP both have a finite optimum solution, then actually the value of that solution is also equal. So the primal LP has a finite optimum if and only if the dual LP has a finite optimum, and also the optimal solution, the primal LP and the dual LP's optimal solution, primal opt and dual opt, are also equal. So what we were talking about right now was we were trying to obtain a lower bound for this primal LP using the dual LP, but actually turns out that yeah, it's not just a lower bound on the solution of this primal LP. It's actually the exact solution. If you solve the dual LP, you will actually obtain the exact solution to the primal LP as well, assuming that uh, the LP is feasible and finite and has a finite solution. So this theorem is a very strong theorem. It's called strong duality, and there is a corresponding weak duality theorem, which just says that if both primal LP and dual LP are feasible, then primal opt is greater than equal to dual opt. Yeah, which we already know because of the lower things. Also, one thing to note here is that so why are we even talking about weak duality if we have the strong duality theorem? Because uh, here it's just here in weak duality we are just assuming that primal LP and dual LP are feasible, and if both are feasible, it can be the case that the primal LP might be feasible as I talked about, but its solution might be unbounded. So it might be the case that primal LP is feasible, but it is unbounded. But uh, yeah, okay, let's just forget that. Okay, sorry. So yeah, so I'm just saying that if both primal LP and dual LP are feasible, then primal opt is greater than equal to dual opt. And so this is a weak duality theorem. And like if you want to see, like, but actually like actually turn out to be equal if both have like finite value. So yeah. Mm. So yeah, so this theorem is called weak duality, and this is called strong duality. So let me just think for a minute, guys, what I was about to say. So I wanted to add something here. So if a primal LP is invisible, it is invisible if and only if dual LP is invisible or unbounded. If it is visible, then dual LP is visible and unbounded, then dual LP is. Yeah. Okay. Yeah. So I don't think I have anything to add here. So this is strong duality, and this theorem is called, if you just assume primal optics greater than equal to dual optics, then this is weak duality. But yeah, so strong duality is like a really nice property which we have for any linear program. And yeah, coming to linear programs, like in general, how do you represent a general linear program? So usually what we refer to is a standard form of a linear program. And what's the standard form of a linear program? Like if a linear program is of this form, where one has to minimize like c1x1 plus c2x2 till cmxm, subject to the constraints that there are some, like, let's say m constraints, uh, like a1 x1 plus a2 x2 till a1m xm is greater than equal to p1. Similarly, some other constraints. So these are like, let's say, m constraints, and yeah, if you and you want to minimize some objective function in which is linear in m, and which is linear in the variables. And note that all of these, and then also another property is that all these variables are greater than equal to 0. So if there are constraints that there are these, so you have to minimize something subject to some constraints, such that there are additional constraints of all the variables being non-negative, then this is called a standard form of a linear program. And note that all of these constraints should be like greater than equal to constraints here. So standard form, essentially you have to minimize the objective function. All the constraints are of the form greater than equal to, and there are also non-negativity constraints on the variable. So if these three things are there, then this is the standard form. And note that this matrix of these coefficients in these constraints is called the coefficient matrix and is denoted by capital A. So yeah, so this is the standard form of an LP, like minimizing an objective function subject to greater than equal to constraints everywhere and non-negativity constraints of the variable. And for this LP, like if this is the primal LP, then actually its dual LP is just given by this form. Like it's not too hard to see yourself how does this come about. You just multiply all these constraints by y1, y2 till ym's, and now the LP is in the variables y1 till ym. The dual LP is in the variables y1 till ym, and it is just, so initial LP was in terms of minimizing some objective function. So dual LP will be maximizing this objective function, and again it will be subject to uh, this constraint matrix. And now these y1 till yms will the non-negativity constraint. So note that this primal LP had the form of minimizing something, and all these constraints were greater than equal to constraints, and all the variables had non-negativity constraints. In the dual LP, it's not a minimizing but rather a maximizing LP, and the constraints are not greater than equal to constraints but rather less than equal to constraints. And all these and also we have these non-negative constraints here also in the variable. So yeah. So yeah, and also like here this was like a11 and a21 till am1 were appearing like in different constraints along with coefficients of x1. But now actually like these a11, a21 actually occur in the same constraint and are multiplied with y1, y2 till ym. respectively. So you can see this for yourself, like how does it come about. Uh, if you know how to write the dual LP, you can just write the dual LP even yourself. But this is a standard way of seeing what is the dual LP to a given primal LP. And then there's this theorem which is a really interesting theorem, which is like complementary slackness condition. So suppose you solve these LPs and you have like some solution like X is the primal solution, primal X is a primal feasible solution, and Y is a dual feasible solution. So we are just talking about feasible, not optimal. But let's just say X is a feasible solution for the primal LP, Y is a feasible solution for the dual LP. So then actually, if you want to check whether X and Y are optimal solutions, then X and Y are optimal if and only if the following conditions are satisfied. These conditions are also called complementary slackness conditions. So what is so one condition is primal complementary slackness. So what is primal complementary slackness? It just says that for all j's from 1 to n, either xj is 0. So note that there were so there are n variables of the form xi. So either the variable xj should be 0 or the jth constraint should actually be satisfied. So in these constraints, like uh, sorry, yeah, in these constraints actually, so CJth constraint, as you can see, like this, the dual LP, and the dual of a dual LP is actually the primal LP again. So so with CJth, you actually have a coefficient of xj attached to it if you are trying to obtain the primal LP again from this dual LP. And then what the complementary slackness condition says is that essentially the CJth constraint uh, multiplied by xj should be 0. So like either xj should be 0 or the cjth constraint should actually be an equality constraint instead of this less than equal to constraint. So yeah. So for each j from 1 to m, either xj is 0 or the jth constraint of the dual LP is satisfied. So it's not either or, it's just an or. Like both of these conditions can also hold at the same time. Like xj can be 0 and this can also be equality at the same time. And similarly, we have a dual complementary slackness condition, which is just like again on the variables y. So y either yth variable is 0 or the yth constraint in the original LP is an equality constraint. And if all these conditions are satisfied, all these primal complementary slackness and dual complementary slackness conditions are satisfied, then actually the given solution is an optimal solution. X comma y are an optimal solution. And yeah, opposite also true. If X comma Y are optimal solutions, then primal complementary slackness and dual complementary slackness conditions are satisfied. Yeah. So this is a like really good criteria. Like so now like because of these complementary slackness conditions, if you are given any solutions X and Y and you want to test whether they are indeed like thus feasible solutions or they are indeed optimal solutions to the LP, you just need to check these complementary slackness conditions. If these hold, then you can easily say that these are also optimal solutions. Yeah. Okay. So after discussing on a somewhat high level, uh, what are these primal LPs and what are these like dual LPs, uh, and like getting an idea of these complementary stackers and all these properties of linear programs, then let's just come to the original task at hand of like using these LPs or linear programs to design good approximation algorithms. So why are we even studying these linear programs? So we are studying these linear programs. We are talking about this linear programming to actually obtain good approximation algorithms for for some problems at hand. And what's the standard template for designing approximation algorithms using linear programs? So now let's just come to that. What's the standard template to solve such problems? So for example, suppose I want to design an approximation algorithm for vertex cover using linear programming. So like note that the vertex cover problem can, so this was also discussed in the lectures, that the vertex cover problem can be written in terms of an integer linear program. So what's an integer linear program? So like suppose for every variable v in the graph, uh, we actually assign a variable xv, which is either 0 or 1. So if it is 1, then we take the xv into our vertex cover. If xv like if xv is 0, then we do not take v into our vertex cover. And now we want to minimize the number of vertices, so we want to minimize the sum of this. And what should be the constraint? So constraint is that the solution should be feasible. And what do we mean by feasibility? Here, feasibility means that in a vertex cover, feasibility means that every edge should be covered by at least one vertex in the solution. So for every edge, we need to ensure that if its endpoints are u and v, uh, either u lies in like you should either u lies in the solution set or v lies in the solution set or both lie. So what this means that xu plus xv is greater than equal to 1, and this should hold for all the edges. And then we can say that it is indeed a valid vertex cover. And all these xv's take either 0 or 1s. So this is how you can actually write the vertex cover problem in form of a integer linear program. So why is it called an integer linear program, not just a linear program? Because here we also have these constraints that xv can only take the value 0 or 1. In a standard linear program, we just say that the variables xv should be non-negative or something. So the variables are continuous in normal linear programs, but in integer linear programs, the variables are discrete here. And yeah, so if you are able to solve this integer linear program, then of course you have solved the vertex cover problem. And that's why uh, integer linear programming is actually an NP complete problem. But what is really interesting is even though integer linear programming is NP complete, but actually solving these kinds of linear programs. Like so, we have not discussed this. There's a whole theory, like a very deep theory of actually solving these linear programs in polynomial time. So for a long time, it was not known whether even these kinds of programs can be solved in polynomial time. But through a lot of through efforts over the years, it was discovered in 80s or like 70s that these linear programs can be solved in polynomial time. So even though integer linear programs are NP hard, solving these linear programs is actually uh, in P in the class P. So if the variables are like continuous, then these linear programs can be solved in polynomial time. So then maybe it suggests some kind of an approach. Okay, like integer linear programming is NP complete. But what if instead of looking at this integer linear program, I just look at the corresponding uh, non-integer or the continuous linear program, which is also called a relaxed LP usually. So like essentially you had this ILP, so you do not change any of the constraints of the ILP. You just ensure that instead of saying that XV was just 0 or 1, you say now XV can lie between 0 and 1 as well. And this is what you call a relaxed LP, because now this is a linear program. And now this can be solved like uh, in polynomial time. How and but however, it does not mean that we have solved the original problem at hand, because this solution can take like even fractional values, not just integral values. And it might be possible that if we take these kinds of fractional values, then we have not actually obtained the optimal solution. But so it's not like exact that one can recover optimal solution from these fractional solutions. So that's why solving these relaxed LPs does not mean we have solved ILPs as well. However, it can be clearly seen that so in this ILPs you can just take the value 0 and 1, and you're minimizing some objective functions with respect to some constraint. But now you are allowed to take even further values other than 0 or 1. So what this means is that the objective functions value can go even lower than the value of ILP, since this is a minimization problem. So what this means is that the value of optimal solution of the linear program will actually be less than equal to the value of the optimal solution of the integer linear program, because in linear program you are taking all the continuous values between 0 and 1 as well. And so you can your minimization LP can go even lower than the integer LP. So the LP opt, which is like the solution for the relaxed LP, is actually less than equal to the actual opt. So what this gives us is a lower bound on the value of opt. So opt was the actual solution, and we do not actually obtain the optimal solution directly using these LPs, but we obtain a good lower bound on these opt values, and that can help us. Maybe a good lower bound can help us design some good approximation algorithms for the problem. So yeah. So LPs are solvable in polynomial time. However, solution is fractional in general. So what we do is we try to round the fractional solution to obtain an integral solution, which is somewhat approximate to the given optimization problem. And this rounding part is like, it's a very high level term. And this rounding is like, so this is a very high level framework of how can one use linear programming to solve, like, to design approximation algorithms for NPR problems. But this does not mean that this is easy at all, because this rounding of fractional solution is really problem dependent. For every problem, you'll need to round the solution in different ways. And and that's where the novelty lies in designing approximation algorithms using LPs. So some further terminology. So yeah, so what's an integrality gap of a linear program? So integrality gap is nothing but so give for over all instances, over all inputs to the suppose we like, so over all the input instances to the linear programs, the maximum value which opt of I divided by LP opt of I can take is also called the integrality gap. So if this is equal to alpha, then what this actually means is that there exists an instance where LP opt is like uh, uh, alpha versus lower bound. Like, so this means that opt of I is like, so let's say this value, like the supremum is attained at the value like I star, then this means that opt of I star is alpha times LP opt of I star. And what this essentially means is that uh, what this will essentially ensure is that uh, if you try to use the LP which you have designed for the given problem at hand, then for that problem, uh, using that specific LP for which you have designed this LP opt, you cannot obtain better than an alpha approximate algorithm, because there exists an instance on which this ratio is actually equal to alpha. So you cannot go beyond alpha for this instance, because this LP opt was the thing which was providing a lower bound for you. So you maybe need to augment this lower bound with something else to obtain a ratio better than alpha. But just this thing will not suffice. So that's why, like, sometimes what happens is maybe one linear program has an integrality gap of alpha, but some other linear program of the same problem has a uh, integrality gap of alpha prime smaller than alpha. So even designing the so even designing an appropriate linear program for the problem at hand is also a challenging problem. It's not always true that it might not always be the case that the linear program, like, there can be multiple linear programs for the same problem. So it might be the case that the one you come up with might have worse approximation guarantees, and some other linear program might have a like better integrality gap or something. So yeah. So so the novelty lies in designing the linear program as well as rounding the linear program. Yeah. Another approach I used, so right now this approach is like rounding the solution obtained by linear program to design like the approximation algorithm. Another approach used to design approximation algorithm using these solutions to linear program is using the LP and its dual LP to analyze a combinatorial algorithm or to design a combinatorial algorithm. This is also called dual fit. And yeah, and this was discussed in the lecture videos as well. So you may as well watch the lecture videos for thorough analysis. So I won't be going over the thorough analysis for this, but yeah. So it was discussed in the lecture videos on how to use dual fitting to analyze greedy set cover algorithm. So what was the greedy set cover algorithm? Maybe just as a reminder, so we discussed this algorithm last time. So set cover problem was like given uh, a universe U and some subsets of the universe U. Then the set cover problem asks us to find the smallest collection of sets such that each element of U occurs in at least one of the sets of the collection at hand. This is what is called the set cover problem. And there was this greedy set cover algorithm, which was just the algorithm was just uh, at every iteration you just pick the subset from the original collection available to you. You just pick the subset which maximizes the ratio of you select the subset which maximizes the number of uncovered elements till now. You select the subset which covers most number of uncovered elements, and you do this for every iteration, like till you cover all the elements of the universe U. And it was in the last week's lecture, it was shown that this algorithm actually is uh, log n approximate. And one can so last time there was an argument using price functions and everything. So actually we'll see a more standard way or a better way, not a better way, but yeah, a more standard argument of like how does this argument of price function even come about. So this was discussed in this week's lecture. So actually, what happens is what the price functions which were discussed in the last week's lecture are actually nothing but the dual variables to the primal set cover problem, and that's from where those price functions came about. And so in this week's lectures, there was discussion about analyzing the same greedy set cover algorithm. Uh, uh, using these LP ideas. So essentially using dual fitting to analyze the greedy set cover algorithm. And again, we use the price functions, and the analysis actually is quite similar to the analysis done previous in the previous week. But here, like now, actually, the idea of using these price functions becomes more intuitive if you look at this dual linear program. Last week, it would seem that okay, it's very arbitrary how do these price functions even come about, but actually there's a very good basis for these price functions. It's from these kinds of linear programs. So maybe just discussing on a high level, so what was done to analyze greedy set cover algorithms. So first, what we'll do is, so if we are given the set cover problem at hand, let's just first design integer linear program for the set cover problem. So what will be the integer linear program? So yeah, so it's just uh, so we have to minimize so we can assign for every subset in the collection given to us, we can assign a variable xs. So if x of s is 0, then we are not actually selecting that subset. If x of s is 1, then we'll actually correct that subset. So now yeah uh, the cost of the selected subsets will be nothing but a summation of c of s times x of s. And what are the constraints? So constraints are essentially whatever subset you choose, they must cover all the elements of the set U. So for all elements in the set U, uh, at least one of the subsets containing the element E should be selected in our collection as well, or our solution as well. So that's why summation of x's such that for all s such that E belongs to S should be greater than equal to 1. And xs is either 0 or 1. So this will be the ILP formulation for the set cover problem. And if you try to relax, so what will be an LP relaxation for this problem? So in an LP relaxation of this problem, yeah, all these constraints remain the same. It's just that this xs becomes, instead of being between 0 and 1, one can just say it is between, like, instead of being just 0 or 1, it is like between 0 and 1. And one can show that like xs being less than equal to 1, that constraint can actually be removed because it's a minimization problem. If xs is greater than 1, you can actually bring it down to 1 without changing the quality of the solution at hand. So that constraint is redundant. So just this constraint is actually what is useful for us. The xs is greater than equal to 0 constraint. So this is the primal LP for the set cover problem at hand. And then what will be its dual LP? So for dual LP, so since these constraints are all for each element E in the universe U, so we'll associate a variable YE for each of these elements. And then what will the dual LP look like? It's just about maximizing Y of E's over all E's in the universe, uh, subject to the constraint that for all subsets in the input, summation of Y of E's should be less than equal to cost of that subset. Yeah, and then non-negativity constraints on the variable Y. So yeah, and note that now you'll see that this Y of E is actually look very similar to the price function which we discussed last week as well. These Y of E's are nothing but actually those price functions which we discussed. And usually like if the coefficient so if the coefficient matrix has only non-negative entries in the primal LP, the minimization LP is usually called the covering LP and the dual LP is called the packing LP. Because like in the set cover also all these coefficients have non-negative entries. So we are covering something and like in the maximization LPs we are trying to fit some solution up to some certain upper bounds and that's why it's called usually a packing LP. So this is again some terminology like usually like it's a very standard terminology, so one should know about it, and it's not really very hard to understand why is this the case. So yeah, so yeah, so and then from this, it was discussed in the lecture videos like using this dual LPs, one can actually reanalyze the same algorithm discussed last week also, and uncover that again like uh, the set cover, uh, the greedy set cover is indeed log n approximate. And the ideas are almost identical to last week's videos where these y's are nothing but price functions. And then, so we'll not be going over the analysis again because these have anyways been covered in the lecture videos. So you should watch the lecture videos for this analysis in detail. Yeah. And then after this, as the last topic of the lecture videos, then there was a discussion about using this dual fitting technique for the set multi-cover problem. So in the set cover problem, every element just needed to be covered at least once. But now what if every element needs to be covered more than once? This is called the set multi-cover problem. What is the set multi-cover problem? Suppose you are given a universe U and a collection of subsets, and like each of these subsets has some costs, and then also for each element in the universe U, there is some value RE. And now what one has to do is one has to select some subset S1 prime, S2 prime till Sk prime such that for all elements in the universe U, E is present in at least RE subset. E is present in at least RE sets in like S1 prime till Sk prime. And the summation of the cost of these sets is actually minimized. So this is the set multi-cover problem. And again, like one can think of like some additional constraints. Although in this problem, like there was not a discussion about the uh, additional constraints. I think so. There can be constraints like what if we are allowed to choose a set more than once? Like right now in the set multi-cover problem, what was discussed in the lectures, I don't think there was any discussion about that. But yeah, so right now in from the lecture videos, there was only discussion about maybe selecting these sets. Uh, yeah, you are allowed to select each of these subsets at most once. It's not like you can select a subset, one of these subsets more than once. So, but another variant of this problem can be like one is allowed to select some subsets, let's say more than once also. So you can select this S1 two times, three times, four times, or something like that. But in the lecture videos, the variant which was discussed was like every subset is allowed to be selected at most once. So, yeah. So what's a greedy algorithm for set multi-cover actually like and it can be analyzed using dual fitting and yeah, and was discussed in the lecture videos. So an element E is alive if it appears less than if it appears less than RE many sets. if it appears in less than RE many sets picked so far. So however number of sets you have picked, yeah, if the number of sets is like less than RE, then E has not yet been covered fully. That's why it's called alive. So in every iteration, the algorithm picks the most cost-effective set. That is the set with minimum average cost per alive element. So you just see like what are the alive elements, and yeah, so what's the greedy algorithm for the set melting over? So you just see mm, uh, so you just see uh, the number of alive. You just see what elements are actually alive elements, and from the remaining subsets which you have not picked, select the or from the remaining sets which you have not picked, select the set with minimum average cost per alive element. So again, like kind of saying like average cost per uncovered element, where this uncovered means like kind of uncovered is changed to unalive because like uncovered is changed to alive because like mm, it has been covered sometimes but not RE many times. So yeah, and then the algorithm halts when no element is actually alive. And it was shown in lecture videos using dual fitting that this kind of a greedy algorithm. So this greedy algorithm is again quite similar in spirit to the set cover algorithm. We have just changed like checking if an element is covered at least once to checking if the element has been covered at least RE time. Showing the lecture videos that this algorithm using dual fitting can be shown to be like again Hn approximate. Hn is just the nth harmonic number, which is just order of log n. So this algorithm is actually log n approximate for set multi-cover. So yeah. So this was all which was discussed in the lecture videos uh, for this week. So yeah, since I guess now no one is in the session to ask any doubts, so I guess we can move on to the problem statement, like some problem which I prepared for this week. Yeah. Um, so let's look at the first problem. So first one says that suppose an approximation algorithm runs in time polynomial in the input size, comma log of 1 over epsilon to output a 1 plus epsilon approximate solution to the given problem. Then the algorithm is a FP task. So this should be an FP task. Is this true or false? So, essentially the problem asks us, okay, suppose we are given an algorithm which runs in time polynomial in input size, comma log of 1 over epsilon. And is that algorithm an FP task? Is this true or false? So what was the definition of FP task? We had discussed this previously as well. So in an FP task, yeah, in an FP task is an algorithm which runs in time polynomial in n, where n is like the input size, as well as 1 over epsilon. Whereas we are given that the algorithm runs in time polynomial input size and log of 1 over epsilon. But actually note that yeah, so like one possible silly mistake here can be one might think, okay, like an FP task should run in time polynomial in input size and 1 over epsilon, but this algorithm runs in time polynomial in input size and log of 1 over epsilon. So that's why it's not an FP task. But this is not actually true because if an algorithm is this is because like log of 1 over epsilon is anyway smaller than 1 over epsilon. So like this complexity is anyways lower than the polynomial complexity of 1 over epsilon. So in fact, this is even a faster algorithm than any other FP task. So this is also in FP task only. So this algorithm is also an FP task because uh, log of 1 over epsilon is actually like because log of 1 over epsilon is actually faster than 1 over epsilon. So since log of 1 over epsilon is order of, yeah, it's not like it's like strictly smaller, like small o of. 1 over epsilon as the algorithm runs in time bounded by a polynomial in input size, comma 1 over epsilon. So, the algorithm runs in time polynomial in input size is 1 over epsilon, and hence the algorithm is data f beta. And the statement is. So yeah, so it is true actually. Okay. So coming to the second question, then the second question asks us solving a linear program is NP-hard. Is this statement true or false? So actually, we just talked about it that linear program. So this is indeed the benefit of using linear programming. Like, why are we even able to use linear programming to design approximation algorithms? It is because solving a linear program is polynomial time. Even though it's not direct, you guys might not know like how do we solve a linear program. Yeah, because there exists like very sophisticated algorithm for this. But yeah, solving the linear program is indeed uh, it is like a polynomial. It can be solved in polynomial time. So the linear, so, like not always, but mostly like solving a linear program is like not NPR. Sorry. And yeah. Yeah, so not yeah, so linear program actually can be solved in polynomial time. It's the integer linear programming which is NP-hard. So that's why this statement is false. Linear programs can be solved in polynomial time, and integer linear programs are not solved. इन दोनों पे मैंने मैथ ओवर फिट कर दिया ओवर फिट नहीं ट्रेन कर दिया लाइक सेम न्यूमरेटर या एंड देन अगर मैं डेल्टा टी बाय 2 पे अगर मैं कुछ प्रेडिक्शन कराना कैन वी डू दिस discussed possibly in the lectures that integer linear programs are actually NPR. So you also might like so you just have to take this for granted for now. Like linear programs can be solved in polynomial time because so how do we solve them? The algorithms for solving these linear programs is actually out of the scope of this course at least. But one can take this as a platform. Yeah. Okay, so coming to the third question then. So third question says that for a linear program, if the value of the primal solution is unbounded, then the dual LP is infeasible. Is this true or false? So actually we talked about the strong duality and weak duality. We just said that okay, if the primal solution is feasible and finite, then the dual solution is feasible and finite. But here we are given that primal solution is actually feasible, but it is not finite. It is unbounded. Yeah. So the primal solution feasible, but its value is unbounded. Then what happens to the dual LP? So one might think that okay, like maybe uh, dual LP might be feasible and unbounded, but actually it is not the case. Like in this case, like I don't think it has been discussed in the lectures properly, but this is something which you should know that that in this case dual LP, if the primal solution is like unbounded, then dual solution will always be infeasible. So yeah. So this is true actually. So like this is a property you should just like know. Like I don't know if it has been discussed properly in the lectures. I don't think it has been, but I think this is very important to know that. Yeah. True as the following conditions hold. So these conditions actually hold, and so yeah. So like this is actually true, and what are the conditions which you can actually, so these like uh, yeah, primal solution is feasible and finite. In that case, actually, uh, dual solution is also feasible and finite. So this is a strong duality which you talked about. And however, like if primal solution, so there's another case that if primal solution is feasible and unbounded. So what happens in this case? In this case, if primal solution is feasible but unbounded, then this means that dual solution is uh, infeasible. And the third case is primal solution is infeasible. Is infeasible. Then actually, dual solution is either uh, feasible and unbounded. So either it is feasible and unbounded or infeasible. So yeah. So these are the conditions shown. So if primal solution is feasible and finite, then dual solution is feasible and finite. If primal solution is feasible and unbounded, then actually dual solution is always infeasible. And if primal solution is infeasible, then dual solution is either feasible and unbounded or it is infeasible. And yeah, like you can replace these primal, like these conditions hold symmetrically for dual as well. So if you replace this primal by dual and dual by primal, the same things will hold. Like if dual solution is feasible and finite, then primal solution is feasible and finite. If dual solution is feasible and unbounded, then primal solution is infeasible. And if dual solution is infeasible, then primal solution is actually either feasible and unbounded or just infeasible. So yeah. So these are things like maybe not they have not been discussed in the lectures properly, but they are like very important. You should keep these in mind, in my opinion. Yeah. Okay. Now coming to the fourth question. So suppose we are given a maximization problem P, and for that problem, P1 be an integer linear program and P2 be its LP relaxation. Uh, so since and let ILP opt and LP opt denote the optimal values of P1 and P2 respectively, then is the following statement true or false? And what's the statement? ILP opt is greater than equal to LP opt implies ILP opt is equal to LP opt. Let's just see. Okay, so we know that yeah, the given problem is a maximization problem, and P1 is an integer linear program, and P2 is its LP relaxation. If P2 is the LP relaxation of the maximization problem, then it means that the optimum solution for this LP relaxation, because because integer values are just subsets of these continuous values. So this P2 can take more values than the program P1. And so and since the maximization problem, so the optimum value of P2 will be at least the optimum value of P1. So P is a maximization problem. Uh, so what we know is that yeah, we can deduce that LP opt will actually be greater than equal to. So yeah, so this is something which we already know because P is a maximization problem. So this thing is actually true. because it is a maximization problem. Uh, and so this is something which is already known. And now so we know that LP opt is greater than equal to ILP opt. But if we are also given that ILP opt is greater than equal to LP opt, if ILP opt is greater, so let's just call this statement as maybe, let's just call this as maybe one. And yeah, and if we are given that ILP opt is greater than equal to LP opt, what's going to happen is then like if ILP opt is greater than equal to LP opt and is if like LP opt is greater than equal to ILP opt and ILP opt is greater than equal to LP opt. So what this means that if x is greater than equal to y and y is greater than equal to x, it can only happen when x is actually equal to y. So what we get is from 1 and 2, we get that actually the values of these should actually be equal. And yeah, so and this is what is asked in the problem. ILP opt is greater than equal to LP opt implies ILP opt is equal to LP opt. So which is true in this case. So hence the given statement is true. So the answer to this is true. Okay, then moving on to the fifth question then. So in the fifth question, like so this is the last question for the day. So suppose an LP has 5 variables taking only non-negative values and 10 constraints other than the non-negativity constraints of the variable. How many constraints does the dual LP have? So maybe let's just look at how did we form. Let's just revise how did we formulate a dual LP from a primal LP. So if primal LP had like n variables and m constraints, n variables and m constraints, then what happened was in the dual LP, like these constraints now corresponded to variables. So in the dual LP, we had m variables and all these original variables corresponded to constraints, and then we had n constraints, like, and all these non-negative constraints were still there. So apart from these non-negativity constraints, the number of constraints and variables gets interchanged. So primal LP had n variables and m constraints. The dual LP has m variables and n constraints. So, and of course, we are ignoring the non-negativity constraint. Yeah. So, yeah. So if the question is like other than the non-negativity constraints, because these constraints are non-negativity constraints are also actually constraints. So if we are just talking strictly about like the non ex about the constraints excluding these non-negativity constraints, uh, uh, then that question makes a bit more sense. So if the LP had 5 variables and 10 constraints, then the dual LP, like excluding these non-negativity constraints, here also we had excluded these non-negativity constraints. Uh, yeah. So then yeah, maybe so the primal had like 5 variables and 10 constraints. So the dual will have 10 variables and 5 constraints. Non-negativity constraints of the variable. Uh, Okay, what happened? Okay, yeah. Apart from the uh, primal we have 5 variables and 10 constraints. And what this means is that um, apart from the non-negativity constraints of dual variables, uh, the dual LP will have like number of constraints and variables that get interchanged between primal and dual. So it will have 10 variables and 5 constraints. So the dual LP only has 5 constraints. And just one thing to note, like so the answer is just 5. So the dual LP will just have 5 constraints because variables and constraints get interchanged. But one thing to note is that if one is asked about total number of constraints, not just like if one has to include the non-negativity constraints of dual variables, mm, then what will be the total number of constraints? Then the total number of constraints will be nothing but like so we had these 5 normal constraints, and then for each of the dual variables we'll have one non-negativity constraint. And how many dual variables there are? There are 10 dual variables, so there are 10 non-negativity constraints. So this is just 50. So yeah. So yeah. So note that uh, yeah, even though in this question we were just asked about the non-negative constraints of dual variables, so they are just 5. But if one is asked about like total number of constraints, where you also have to include the non-negativity constraints, the total number is just the sum of the number, like number of variables plus number of not like these constraints. So 10 plus 5 is 15. So this is the answer if one asks about total number of constraints. So, okay, then I guess this was it from my side. So, we discussed about like we discussed like 5 problems related to this week contents, essentially like approximation algorithms and linear programming. And yeah, we also discussed all the topics which were covered in this week's lectures, like what are F betas, what is LP, like what are dual LPs, and what is like how do we like round LPs, or like on a high level, how do we use dual fitting to analyze algorithms? And like, yeah, what is complementary slackness and everything. So yeah, uh, I guess this was it from my end, guys. So since there is no one present in session right now in person, and we have a bit of time left, so maybe I'll just wait for like 5-10 minutes if someone wants to join the session and ask some doubts. So if no one joins in like next 5-10 minutes, then maybe we can close the session. But till then, I'll just mute myself. Okay, so I guess like since no one has joined the session for any doubts, so I'll be closing the session then. So once again, thanks a lot to everyone who's watching on YouTube. Hopefully, I'll see some of you guys in person next week, same timings, Tuesday 6 to 8 p.m. So yeah, see you next time, guys. Thanks a lot for watching. Bye bye.